Welcome everyone. Thank you for joining us for today's webinar, Verification Automation Using AI. I am a host, Mamta Arya. Agnisis is a leader in electronic design automation, delivering solutions for complex design and verification problems in system development. This webinar will showcase how AI helps identify verification gaps, optimize simulation generation, and reduce redundant simulations, leading to faster coverage closure. This session will go deep dive in how AI-driven verification solution can analyze design, specification, RTL, and register description to automatically generate UVM components, test scenarios, assertions, and coverage models. As a reminder, everyone will receive an email with instruction on how to review the PDF and recording for today's webinar. We will also be taking some time at the end of the webinar to answer your questions. So please do use the question panels on your screen. Please welcome our presenter for today's webinar, Nikita Gulia. Nikita is a senior product engineer at Agnisis and has 8+ years of experience in this field. Over to you, Nikita.
Thank you for the introduction, Mamta, and welcome everyone. I hope this webinar is useful for all. Today, we'll walk through how AI Square transform specification into a complete automated verification environment. We'll start with the fundamentals of verification and its challenges, then move into how AI Square addresses the verification bottleneck. From there, we'll deep dive into automated bus verification, generated register sequences, coverage automation, including LUT based and cross coverage, along with custom sequences. We'll also show the output directory structure so you understand what exactly gets generated. Then we'll move into the live demo, including the demo design, demo video, and coverage report, and finally wrap up with the key benefits. So let's get started. The main purpose of verification is to ensure that the design correctly meets all the system requirements and specification. Essentially, we want to make sure that what we have designed behaves exactly as intended. Verification is also important to check the correctness of protocols and interfaces. There are different approaches to design verification. One common method is logic simulation, where we verify the detailed functionality and timing behavior of the design. This helps us understand how the design behaves under different scenarios. Another approach is functional verification, where we use functional models that represent the expected behavior of the design and compare them against the actual implementation. We also have formal verification, which mathematically checks the designer's functionality against a reference or golden model, ensuring correctness without relying on simulation. Finally, to ensure we don't miss any scenario, we use comprehensive test cases to improve coverage and validate all possible behaviors of the design. Verification is one of the biggest challenges in the industry today, especially as design complexity continues to grow. Another major challenge is the high cost associated with verification. In fact, nearly 70% of the overall development efforts goes into verification. This includes not just engineering efforts, but also the cost of tools, simulation licenses, and computing power required to run large-scale simulations. There is also a significant difficulty in terms of resources. There is often a shortage of experienced verification engineers, and a lot of work still involves manually translating design intent into test code. From a reuse perspective, we face challenges both horizontally and vertically. So horizontally, verification is just one part of the overall flow. We also have firmware prototyping and validation teams, but typically these teams work in different environments, use different languages, and do not share code efficiently. Vertically, reuse across different levels of design is also challenges. For example, test sequences or register specification created at the IP level are not always directly reusable at the subsystem or system level. This is due to differences in bus protocol configuration and even how transactions are executed. All these factors together make verification a complex, resource intensive, and more fragmented process. So, where do verification teams typically spend most of their time? First, a significant portion goes into understanding the design intent. Before writing any test, engineers need to fully understand how the design is supposed to behave, as shown it's 10% here. Next is creating the verification plan, where we define what needs to be verified, the scope, and the overall strategy, which is also you can see 10% here. A large amount of time is then spent on implementing and debugging the verification architecture. This includes building the test bench, setting up environment, and ensuring everything is connected correctly, which is 20% as shown. However, the biggest chunk of time usually goes into implementing and debugging tests. Writing test cases, fixing failures, and refining scenarios is a very time consuming process, which is 30% as shown. After that, team spends time running regression and debugging failures across multiple test runs, which are repetitive and resource intensive. Finally, there is coverage review, where engineers analyze whether all scenarios have been tested and identify any gap. So here we talk about the core problem we are trying to address, the verification bottleneck. Traditionally, verification approaches are largely manual and do not scale well as design complexity increases. As designs grow bigger and more interconnected, the effort required for verification grows disappropriately. In fact, up to 70% of the total chip development time is spent in verification. There are several key challenges contributing to this. First, specifications are often too large and fragmented, making them difficult to interpret and consistency across various teams. Second, a significant amount of effort goes into manual UVM test creation, which is both time consuming and prone to errors. Third, verification typically involves multiple iterative debugging cycles, where issues are found, fixed, and verified repeatedly. All these lead to serious consequences, including delays in time to market, increased, increased risk of human error, and schedule uncertainty. This clearly shows the need for a more scalable and automated approach to verification. The architecture behind AI Square. First, we have document ingestion. AI Square is capable of taking in multiple specification formats, such as Word, PDF, System RDL, IP Exact, or IDSCF, and extracting the semantic structure from them. This allows it to understand not just the content, but also the intent behind the specification. Second is knowledge representation. AI Square goes beyond simple text processing by building structured representations and establishing causal relationships. This enables it to generate concrete and verifiable reasoning for every assertion rather than relying on surface level interpretation. Third is UVM generation. Using a combination of logic driven methods and LLM guided reasoning, AI Square automatically generates structured and standard compliant UVM test sequences, reducing the need for manual test development. Overall, this represents a fundamental shift from traditional manual verification effort to AI assisted engineering, where productivity and consistency are significantly improved. So, The solution, AI Square, a complete automated verification system. Let's talk about what AI Square brings to the table in terms of both design and verification. On design side, AI Square is capable of generating the key design components such as IP register logic and the corresponding wrapper modules. On the verification side, AI Square automatically generates the complete UVM verification environments. It also supports multiple industry standard bus protocols such as AXI FOFUL, AXI Lite, AHP, APB, Avalon, Tiling, and even proprietary buses. AI Square can execute standard UVM sequences and tests, and also supports automatic mirroring of register, ensuring synchronization between the design and the verification model. In addition, it generates sequences for register verification, covering all types of register, simple register as well as special registers. Beyond that, AI Square enables the creation of custom sequences also in Excel format, IDSNG, Python format, or even PSS. It also supports generation of custom checks for these specification, ensuring that the verification is not only automated but also aligned closely with the intended design behavior. AI Square approaches verification as a process of reasoning over knowledge rather than simple pattern matching. Instead of just reaching to input, it builds an understanding of the design. It generates both test and test benches automatically, but more importantly, it understands the design intent, not just to observed behavior. AI Square is also capable of handling ambiguity and even contradiction within the specification by interpreting them in context, which is something traditional flow struggles with. It frees up engineers to focus on creative verification problems. On the right-hand side, you can see a snippet of IDS collaboration framework where the single source of truth, a specification in IDS CF, is being written, from which automatically output can be generated. It is now in the slide, it is shown how AI Square translates high-level test intent into actual UVM sequences. On the left-hand side, we start with the test intent. For example, we want to program specific registers, apply constraints such as packet length limits, and check certain behavior like the busy signal and packet generation conditions. These are typically written at high level, describing what needs to be verified rather than how to implement it. And on the right-hand side, we see automatically generated UVM sequences. AI Square takes that intent and converts it into structured, standard compliant UVM code. Typical block in an SoC. Let's start from the very basic. So inside the RTL block wrapper on the left hand side, we have the register RTL block, which is typically auto-generated with tools like IDS. This block interfaces with the register bus and handles all CSR related functionality. And on the right hand side, we have the user application logic, which is user created RTL. This represents the core functional logic of the IP. Between these two blocks, we have well-defined interfaces. The register and signal interface allows communication between register block and the application logic, while the external interface connects the block to the rest of the system. Even though register may seem simple, they actually consume substantial amount of time. Around 25% of the effort is spent on addressable register-related tasks. A large portion of effort goes into building and maintaining the register space, ensuring that all registers are correctly defined, mapped, and accessible. What makes this even more complex is that a single register exists across multiple representations. It may be described in format like Word, Excel, or other specification tool, documented separately, implemented in Verilog, and then verified in UVM. Because of this, even small change to register needs to be reflected across all these representations and communicated to multiple teams. So while registers appear simple at first glance, managing them across entire design and verification flow is actually challenging and time consuming. So here you can see a sample of input specification in IDS CF collaboration framework where a register can be defined with its multiple attributes such as register name, bits, fields, name, software and hardware access, description can be given, and multiple such templates can make a register specification. And automatically, code such as RTL, UVM, headers, sequences, system RDL or IP exact can be generated out of it. Now we've talked about the single source of truth and input specification and the basic DOT and the application logic. Let's move on to the overview of AI Square generated verification environment now. This diagram shows the automatically generated UVM test bench architecture. At a high level, the verification environment targets three layers: the bus layer, the register or IP layer, and the hardware application layer. The idea is to verify the complete system from protocol interaction to register behavior and finally the application logic. All the components shown in orange and gray are automatically generated, while the blue blocks represent the user RTL. This highlights the key advantage. Most of the verification infrastructure is created automatically from the specification. Starting from the list, we have the register bus agent, which includes components like bus adapter, sequencer, driver. The agent is responsible for converting the register level transactions into bus level transaction. And here, bus protocols which are supported are AXI, AHB, and APB. In the center, we have register model and model updater. So the register model represents the expected state of the register, while the model updater keeps it synchronized with the actual hardware by observing updates through the tapper interface. The tapper interface connects the verification environment to the DUT by tapping into the hardware signals. This allows real-time monitoring. We also have signal interface and checker. So the checker validates the behavior of the design, and it can include automatically generated assertions based on the specification. The dotted line you see represents the system Verilog transaction used for communication and event tracking. On the right-hand side, we have VIP agents and sequence libraries, which handle protocol level verification. At the top level, the UVM test integrates all of this, including configuration, coverage collection, and sequence execution. Overall, the key takeaway is that complete end-to-end verification environment is generated automatically, that too from a single specification, covering protocol, register behavior, and system-level interactions, significantly reducing manual efforts and improving consistency. Now let's look at the reg model. A reg model is structured software representation of the DUT's register space. It can include individual register files, memory, and hierarchical blocks. Each register in the model directly maps to a hardware register, enabling accurate read, write, mirror, and checking operations in UVM. Traditionally, the model is written manually using UVM RAL, which is time-consuming and error-prone. With AI Square, the reg model is automatically generated from the same executable specification used for RTL. This guarantees consistency between design and verification teams. The registers in hardware can be volatile, meaning their values can change due to internal logic, not just software writes. To keep the register model aligned with the DUT, the model updater is used. And whenever a hardware event occurs, such as internal write or state change, the model updater captures the updated value through the tapper interface. And the tapper interface, in turn, plays a critical role in maintaining synchronization between hardware and the verification environment. It taps or captures the internal value directly from the hardware register interface inside the DUT. The component interface defines the hardware interface between the user-defined application logic and wrapper block. It contains the pins and signals through which wrapper communicates with the outside world, such as control signals, status outputs, or data paths. Now, moving on to automated bus verification as part of overall verification flow. The key idea here is that we are able to achieve near 100% functional coverage for register-focused verification by automating the entire environment generated from the specification. And talking about the coverage collector, uh, it is the coverage is not written manually. Instead, it is derived directly from the specification. For example, LUT definitions in the specification are automatically converted into functional cover points. In addition to explicit definition, the system also integrates implicit cover points into the coverage collectors. And the coverage collector ensures that all valid LUT-defined functional values are exercised during verification, helping achieve comprehensive coverage. Register sequences which are generated automatically include both the positive and negative tests for register access, such as read-only, write-only, read-write, and positive and negative tests of all fields access are generated. There are special accesses such as write 1 to set, write 0 to clear, write 1 to clear, and write 0 to toggle. So such special software accesses are also covered in generating the automatic sequences so that maximum 100% coverage is achieved. Not only accesses, it is not limited to that. For special registers also, such as the lock unlock register, the aliases, and FIFO and indirect registers. So for all these tests and sequences are automatically generated. For memory tests are there, advanced features such as multiple bus domains, checking holes in the adder map, and bus protocol checks such as the entire EMBA family, as you can see here. The coverage collector can also be defined in the specification using LUTs as shown here. And this is inline lookup tables, which can be specified along with the specification. And what the system does is automatically interpret these LUTs definition and convert them into functional coverage points as shown on the right hand side. Each LUT entry is translated into coverage bins inside a cover group. Not only simple coverage, but also it is capable of automatically generating cross coverage as well. In the previous slide, I mentioned how automatic sequences are generated in order to achieve 100% coverage. User can define its own custom sequences also. Now we provide IDS, NG, Excel, Python, or standard PSS, Portable Stimulus Standard based input specification for custom sequences, so that automatically UVM code for those sequences are generated. User do not need to write the UVM sequences inside, just write the sequences, their support of like the hierarchical sequences, structure, fork joints, if else loop, while loops, randomization and constraints. And this is an example of a sample specification for the sequences. Now, what do you get as an output? This is the directory output structure, which is shown here, where from one single specification, DUT can be generated, the RTL output, the UVM RAL, coverage collector, user-defined sequences can be defined from the specification, some interfaces, system analog interfaces, checker. And in this ARV directory, which is automatic register verification, the AI sequences are generated. Apart from that, obviously register sequences, bus agent, updater, environment, test package, configuration package, top instances, and the make files for various industry simulators such as VCS and Xelium and other Questa make files are generated so that it is executable environment. You can just run a simple make file and the simulation is automatically triggered and you get the coverage report. Finally, let's see how things are working in practical. Here is a demo design which we will be showcasing. First, we start with the register specification creation, where the registers are defined in IDSCF collaboration framework. This serves as the foundation of both design and verification. Next, we demonstrate how application logic can be described using natural language instead of writing detailed RTL or test code. The intent of the design can be expressed at a higher level. Based on this input, the system automatically generates the complete verification environment, including test win sequences and all other components. And as a result, we will look into the coverage and we'll show you how the generated environment achieves comprehensive coverage. And overall, this demo walks through the entire flow. So let's look at the demo now.
Okay, for the demo, we have a very small design just to prove the concept. We have a register block, which is represented by these three registers. And then it is talking to a state machine, a very small state machine. And it also has a couple of ins and outs. Now, this is represented in the CF, which is our collaboration framework. In a GUI form, this is the GUI form, where we have all the registers. And also in system RDL, here is the RDL representation of the three registers. This could be as complex as you want. And notice that currently the output is empty. There's nothing in the output directory. And the core logic that you want to connect to the register is in the app logic. And that has the details of the design. The design itself has been specified in a spec document, which is this is the specification. This could be as elaborate as you want. Now, what we're going to do is, first of all, check the spec quality, whether the spec is good, it's good or not. And then we're going to generate from that, we're going to generate the output, the sequences. So checking the spec quality, I click on this and it goes through and connects to our local AI engine, and it's giving issues that it found. We're not going to go into all the issues, But let's go ahead and then generate. But if there were issues, then it would point them out right here. So in the generate phase, it is basically reading in the input spec, parsing, building a knowledge graph, and then generating all kinds of FSM and tests, and then creating the entire UVM environment along with the agents and the sequences, and then we can take a look at it. Now let's go to the output directory. Yeah, in the tool, there is the output directory, and notice now that it is filled. It's got all the things. Let's go into all the details. Let's see, let's say, where is the, yeah, and we can go in the normal Linux as well. Let's look at the timestamp. It was just created. Okay, and then let's run the simulation on the generated file. Actually, before we go to the simulation, let's look at the sequence that got generated. So this is the AI-sec directory, is where all the sequences are. There is the RAL sequence. And then there are sequences for the various inputs. Yeah. And they're all connected together by a master sequence. Yeah. And this is basically being generated from the by reading the input specification. And now let's run the simulation. We're using Questa, thanks to Siemens. And now it's going through compiling everything and running all the tests. And then the coverage, and it's merging all. I mean, we're not running too many times, but here is the coverage is also has also been generated. And now let's look at the UCDB file and look at the coverage. So the cover groups, incidentally, were also generated by the AI. And so now look that based on the specification, we're getting 100% coverage. So I know it's a very small design, but I think it proves the point that we're doing everything using AI in a very controlled sort of way. Thank you.
Back to the presentation, that was Anupam doing a demo for us. And as you saw towards the end, this is the coverage report generated. And you can see that almost 100% coverage is being generated for all the registers and bus protocol as well. Each of the coverage items has been exercised and all bins have been hit, which indicates that verification environment has thoroughly validated the design. And lastly, let's look into the benefits. Summarizing the key benefits of this approach is that first, code is automatically generated directly from the specification, and this eliminates the need to manually write RTL verification code in supporting infrastructure. As a result, the number of manual changes required to significantly reduced, and instead of updating multiple artifacts across design and verification, engineers only need to update the specification. This table highlights this clearly. In a traditional flow, even a small design change like a register access update or address modification requires updates across multiple components such as RTL, register model, sequences, verification checks, and coverage. In contrast, with this approach, the same change only requires updating the specification, and everything else is regenerated automatically. This not only saves time, but also reduces the risk of inconsistencies and errors across different parts of the flow. Continuing with the benefits, focusing on different types of users. If you are new to UVM, this approach makes it very easy to get started. It automatically creates a complete UVM based verification environment. So you don't need deep expertise in UVM or verification to begin validating your design. On the other hand, if you are an experienced verification engineer, it still provides significant value. You no longer need to spend time manually building the verification environment or writing sequences from the specification. Instead, the automation takes care of the repetitive and time consuming task, allowing you to focus on more complex and critical areas of the chip where your expertise is really needed. So, whether you are a beginner or an advanced user, the approach improves productivity and simplifies the verification process. So here talking about Agnisis. Agnisis is a leader in EDA company focused on specification-driven automation with 1,000+ users worldwide and strong customer retention. We help semiconductor teams reduce risk and help having an accurate development. This summarizes the tools we offer. Thank you.
Thank you, Nikita. So we do have some questions for you. Just a reminder to our attendees, if you have any questions about today's webinar, please enter them in the question panel. And now on to your questions. So the first question is, how can user input their specification into AI Square and what input formats are supported?
AI Square supports multiple ways to input specification to ensure flexibility across different teams and workflows. Specification can be created directly within IDS collaboration framework, which is a real-time template-based collaborative environment where multiple teams such as design, verification, firmware can jointly define and edit executable specification. And specification can also be captured in standard languages such as System RDL IP exact or Word Excel as well. In addition, the application logic specification can be in a Word document, PDF files, or even in natural language .txt or .md for AI engine to read.
Okay. So the second question is, how does AI Square help improve coverage, closure, and reduce verification bottlenecks?
Yes. So AI Square is capable of automatically generating coverage models, cross coverage, constraint driven sequences directly from the specification. And it also generates automatic coverage for the CSR register based on its access and functionality. And coverage can also be generated for the hardware software interface, the HSI, based on the bus protocol. Uh, so it gives like the 100% coverage closure, and of course custom sequences is also possible to be generated, uh, so it enhances the complete coverage.
Okay, so the third question is, what role do knowledge graphs and vector database play?
Knowledge graphs capture the structural relationship between the register, fields, interfaces, and behavior, while vector databases enable semantic search and contextual understanding. Together, they allow the system to reason about the specification rather than just process it as a static text.
Okay, so the next question is, what does drop-in and ready integration really mean in practice?
Okay, that might be confusing. So it means teams can bring their existing specification, whether structured or unstructured, directly into the platform without rewriting everything. So the system automatically ingests structures and transforms the content into an automation ready format, minimizing disruption to current workflows.
Okay, so the next question is, how is UVM generated using LLM guided logic?
Yes. So the system combines rule-based verification logic with LLM-guided reasoning to generate structured, standard-compliant UVM environment, and this ensures the output is obviously deterministic, aligned with design intent, and not just generative text output.
Okay, thank you everyone for joining us for today's webinar. As a reminder, everyone will receive an email with instruction on how to review the PDF and recording for today's webinar. If you have any question or would like to view downloads, we invite you to fill the contact form at agnisis.com or send us an email at support@agnisis.com. Stay safe. We will see you next time. Thank you.